Electric vehicles are transforming the automotive landscape as the world shifts towards the green energy. Unlike traditional internal combustion engine vehicles, EV comes with unique engineering challenges like the primarily due to the heavy battery packs and silent operations. This difference demands more than just adapting all the system. The suspension in the EVs must evolve to the support the extra weight, maintain high performance, and delivery smooth ride comfort. As a result, suspension design has become a critical area of innovation to ensure safety, stability, and user satisfaction in modern electric vehicles. One of the biggest challenges in electric vehicle suspension design is managing the extra battery weight. For instance, a Nissan Leaf battery with over 315 kilograms, while a Tesla Model S exceeds 615 kilograms. This added may put serious strain on suspension components like bushings, wheel bearings, and struts, causing them to wear out the faster than in traditional car. In real-world driving, this results in reduced handling precision, poor cornering stability, faster tire wear, and frequent alignment issues. To overcome this, EV suspension system must be specially engineered with the stronger, more durable component to withstand these heavy loads. The suspension system is the critical part of how a vehicle interacts with the roads. It absorbs the bumps and shocks, ensuring a smooth ride while also maintaining tire contact for stable handling, good braking, and overall traction. It supports the vehicle's weight and keeps the ride height consistent. In electric vehicles, suspension becomes even more important due to the heavy battery packs. That's where active suspension system come in. The systems are designed to counterbalance uneven weight distribution and reduce unnecessary motion, which not only improve the comfort and control but also help conserve battery power by minimizing road resistance. The next is the passive. Passive suspension systems are the most common type found in vehicles across Malaysia. They rely on fixed mechanical components like coil springs, leaf springs, and standard hydraulic dampers to absorb the shocks and regulate the movement. While they are cost-effective, simple to manufacture, and easy to maintain, passive systems don't adapt to road conditions, making them less responsive during aggressive or uneven driving. In electric vehicles, passive suspension are used in entry-level models to save costs, but the extra battery, weight often over 315 kilograms, accelerate wear on this component. As a result, EV owners face more frequent maintenance and often turn to aftermarket upgrade for better durability and performance. Next is about the semi-active. Semi-active suspension system offer a smart balance between the passive and fully active setups. They use sensor to monitor road condition, wheel movement, and vehicle body dynamics. This data is processed by the ECU, which then adjusts the damping force in real time. A key technology here is the mechanical damper or MRD. It uses ferrous fluid that changes viscosity instantly when electric current is applied, allowing the damper to settle or soften in milliseconds. This gives EV better handling, less wear on components, and smooth ride quality. One great example, the Magna Ride system used in the Ford Mustang Mach-E GT, proving how reactive and adaptive MRD are for electric vehicles. Now, let's move to active. Active suspension systems are major leap beyond traditional setups. They use sensor, actuators, and an ECU to adjust damping and even vehicle height in real time. The system actively raise or lower each wheel, ensuring maximum comfort and handling. For electric vehicles, this is especially valuable active suspension encounters the acts of heavy battery weight and keeps the vehicle stable during turns and overall steering. It also improves energy efficiency by minimizing unnecessary motion. However, the downside is cost and complexity. Active systems are expensive and weak and frequent skilled technicians for maintenance. That's why they're mostly found in higher and EV, where top-level performance and ride quality are essential.
Channel 1. In a 2022 review by Wu Fenking, electromagnetic energy regenerative suspension system are highlighted as the future for advanced EVs. This system harvests energy from vertical motion using technology like those developed by Boost and Schaeffler, while still maintaining ride comfort. Test results show energy recovery efficiency between 20 to 50% depending on road condition. However, the article has some weakness. It lacks experimental dataset and does not benchmark performance against passive or active suspension system. Also, it fails to measure ride comfort degradation under different conditions like road or terrain. Still, it provides a strong foundation for future suspension innovation in EVs. Journal 2. In a 2024 study by Nguyen, Bui and Lee, the focus is on optimizing electric vehicle suspension using the improved artificial fish swarm algorithm. Key parameters like NVH, damping, stiffness, and pitch were optimized using a half vehicle model in MATLAB, simulating ISO B road condition at 20 milliseconds. The results show major improvement. 15.44% reduction in driver seat vibration, 11.46% in body vibration, and 8.65% in pitch. This proves that optimizing suspension setting greatly enhances ride comfort. However, study weakness is that its simulation only with no real-world hardware validation. It also uses fixed test conditions, which limits how applicable the results are to varied road and speed scenarios. Summary. In Table 2.2, we compare two key journals. The first by Fu, focus on energy regenerative suspension system. Its strength is a comprehensive review of regeneration technologies, identifying to up to 50% energy recovery. However, it lacks experimental data and real-world benchmark. The second paper by Nguyen explore parametric optimization using the improved artificial fish swarm algorithm. It shows strong results with up to 21.5% ride comfort improvement. But the study is entirely simulated based with no real-world testing or variable robustness. This comparison highlight the gap between theoretical potential and practical validation in EV suspension research. 4 posts. Before starting the test, safety is our first priority. All students must wear safety shoes and glasses, and the work area must be free from oil spill and sharp tools. Next, check the lifting equipment, like inspecting hose, air connector, and test the emergency stop button to ensure the 4-post lift is in good condition. Then drive the vehicle slowly onto the lift platform under supervision. Apply the parking brake, and then lock the vehicle before lifting up to 1.2 meters. After that, install the testing post on all 4 wheels and secure them with safety pins. Slightly push the vehicle sideways to confirm it stable. And finally, run the 30 to 60 second simulation to observe suspension movement, sound and vibration, simulating real road condition. Expected result. In this sample, we evaluate a semi-active suspension system on a compact 4-door electric vehicle. The test compare comfort mode versus sport mode using control inputs, 5 Hz sine wave, 20mm pothole impact and lateral pitch input over a 60 seconds cycle for each mode. The expected result show key difference in comfort mode. Vertical wheel travel reach 12mm, pitch angle is 2.2 degree, and the noise is limited to 38 decibel. While in sport mode, the system stiffens wheel travel reduced to 7mm, the pitch angle dropped to 1.1 degree, and the NVH rise to 40 decibel. Short rebound time improved the 140 millisecond in comfort to just 90 millisecond in sport, showing faster suspension response under dynamic driving. Cost estimation. For our suspension testing setup, the total estimate cost is 2.35 million. The most expensive item is the 4-post suspension tester, priced at 1.8 million. This model includes full actuator control for high precision simulation. The next is high sensitivity sensors like accelerometers and LVDT are estimated at 150,000 ringgit, followed by control software and analysis tools such as LabVIEW at 90,000 ringgit. Installation and safety setup costs at 40,000 ringgit, while the vibration isolation system to prevent the interference is adds 60,000 ringgit. Lastly, a 10% contingency fund of 214,000 ringgit is included to cover unexpected expenses. This investment supports accurate real-world suspension for testing in advanced EV research. Our suggestion in this project is based on the test result and recent studies. We propose a suspension design using a McPherson strut at the front and multi-link suspension at the rear. This combination offers a progressive rate coil springs, electrically controlled damper, and isolated bushing. Crucial features for reducing NVH and improving handling electric vehicle. By integrating semi-active damping into this layout, we can balance the comfort of passive system with the responsiveness of active control. Using the 4-post suspension tester, we can fine-tune the setup to deliver a safer, smoother and more efficient ride. This hybrid approach is ideal for meeting the demand of today's EV environment. So that's all, thank you.
In section 4.0, we analyze suspension choices across different EV segments. For segment A, represented by the BYD Seagull City car, the setup uses a McPherson strut in the front and a torsion beam at the rear, paired with compact 15-inch tires, a cost-effective and space-saving design suite for urban use. In segment B, the Tesla Model Y, which is an SUV, uses a double wishbone at the front and multi-link at the rear suspension with the 20-inch tires, balancing performance with comfort. Finally, for the segment C, we use D-Max EV pickup, also use double wishbone and multi-link suspension, matches with 20-inch tires in all terrain, optimized for payload stability and off-road stability and off-road compatibility. This highlights how suspension design vary depending on the vehicle rules.
So we proceed to segment A. Segment A vehicle use a front McPherson strut independent suspension combined with a rear non-independent torsion beam, paired with 175, 60 and 15-inch tire. This configuration strikes a balance between cost efficiency, space optimization and adequate ride quality for urban driving. The McPherson strut, known for its lightweight and simple design, delivers acceptable handling and comfort at low city speeds. At the rear, the torsion beam reduces component count and packaging complexity, freeing up cabin and trunk space. So for Section B positioned as a compact to mid-size electric sedan, features a double wishbone front suspension and multi-link independent rear suspension, paired with 255, 40 and 20-inch tire, low-profile performance tire. This high-performance configuration is engineered to deliver superior handling, stability and ride comfort, especially under dynamic driving conditions. The double wishbone design enables precise camber control during cornering, enhancing grip and steering accuracy. Next, we proceed to Segment C. Segment C is a premium all-electric adventure pickup built with a front double wishbone and rear multi-link independent suspension, both enhanced with adaptive dampers and dynamic roll control. This advanced setup ensures off-road capability, towing stability and smooth on-road refinement. The double wishbone front allows long suspension travel for rugged terrain, while the multi-link rear provides rear axle traction under load. Adaptive dampers adjust stiffness in real time, softening for comfort or firming up for control.
And then for the McPherson strut, is well known for its compact, lightweight design and is especially effective in front-wheel drive vehicles. Its use of progressive rate coil springs and compatibility with semi-active dampers make it ideal for electric vehicles, which demand precise handling and ride comfort due to their low center of gravity and quiet operation. At the rear, the multi-link suspension provides excellent wheel articulation and road vibration isolation, essential for improving NVH, which is noise, vibration and harshness. This combination directly enhances passenger comfort, which is a key priority of EV owners seeking a smoother and a quieter ride. When enhanced with semi-active suspension systems, such as electronic damping, control and isolated bushings, the McPherson and multi-link setup allows precise fine-tuning of ride quality in real-world conditions. These components adapt dynamically to road inputs, improving comfort without sacrificing handling. The use of 4-post suspension test rig further strengthens an engineering process by simulating wide range of road conditions, evaluating system performance in a controlled environment. This ensures that both safety and ride refinement are prioritized, making the suspension system highly reliable and suitable for modern electrical vehicles. The hybrid approach, which is combining active control technologies with proven passive mechanical systems, result in a suspension that is both responsive and reliable. This setup is adaptable across various EV platforms, from complexity to luxury sedans and even utility pickup trucks. In short, the McPherson strut in the front of multi-link and multi-link suspension at the rear is highly recommended for modern EVs. It offers the flexibility and performance needed to handle everything from the urban road to rugged terrain, making it future-ready solution for the evolving electrical vehicle market. In section 4.0, we analyze suspension choices across different EV segments. For segment A, represented by the BYD Seagull City car, the setup uses a McPherson strut in the front and a torsion beam at the rear, paired with compact 15-inch tires, a cost-effective and space-saving design suite for urban use. In segment B, the Tesla Model Y, which is an SUV, uses a double wishbone at the front and multi-link at the rear suspension with the 20-inch tires, balancing performance with comfort. Finally, for the segment C, we use D-Max EV pickup, also use double wishbone and multi-link suspension, matches with 20-inch tires in all terrain, optimized for payload stability and off-road stability and off-road compatibility. This highlights how suspension design vary depending on the vehicle rules.